15 gemstones, so rare they shouldn't exist on Earth. Most gemstones are shaped by chance, a few by pressure, heat, or time. But the stones in this journey, these 15 fragments of the Earth, should not exist at all. They come from conditions too narrow to repeat, from volcanic fractures that open for seconds, from forests erased by geological time, from ancient oceans pulled into the mantle, and from chemical pathways so unstable that one breath of difference would have erased the crystal entirely. Some formed in darkness deeper than caves, others in lightning strikes lasting less than a heartbeat. One survived light only by hiding from it. One exists because the planet briefly allowed a structural mistake. And one, at the very end, rose in silence from the boundary of the mantle, carrying no myth, no history, only the quiet truth that the Earth still keeps secrets even science cannot fully map today. We enter a realm where geology becomes improbability, where beauty is an accident, and where rarity is measured not in carats, but in impossible survival. Welcome to 15 Gemstones, so rare they shouldn't exist on Earth. A descent into the hidden architecture of the planet, where every stone is a contradiction, and every contradiction is a story carved by forces beyond understanding. Ranked 15th, Rhodochrosite Stalactite, the geological memory that shouldn't exist. Rhodochrosite stalactites are not ordinary mineral formations. Their circular pink bands, layered with surgical precision, are geological records so unlikely that their existence challenges the idea of stability within Earth's subterranean environments. Each concentric ring forms only when temperature, flow rate, and manganese saturation remain perfectly consistent for centuries. Slight disturbances erase the structure entirely, yet within a handful of sealed cavities beneath the Andes, that equilibrium endured long enough to create what collectors now call Rosetta chambers. Unlike minerals formed through sudden pressure or rapid crystallization, rhodochrosite stalactites grow through extreme slowness. A manganese-rich droplet falls. It leaves behind a micrometer-thin layer. Another droplet follows the same path, repeating the same gesture thousands of times. If the water accelerates, the stalactite collapses. If oxygen levels change, color is disrupted. If temperature shifts slightly, banding becomes distorted. This precision-dependent growth defines the stone's rarity. The environmental stability required no longer exists in most of the original chambers. Many collapse due to mining, seismic shifts, or hydrological changes. These stalactites are therefore not just minerals. They are preserved conditions of a world that has vanished among Quechua and Aymara communities. The circular bands were interpreted as Earth's internal calendar. Each ring represented a season, a climate cycle, or the imprint of ancestral time. Colonial-era documents describe thin slices of rhodochrosite being used in rituals marking transitions between agricultural periods. Metalworkers in Potosi referred to the most intense red as the mine's heart, believing it recorded the long pulse of the mountains that shaped their livelihood. These cultural associations, rooted in observation rather than myth, position the stone as both ornament and chronicle. Rhodochrosite stalactite slices were once placed in water during full moons. As moonlight passed through the layered manganese bands, the reflected color variations were read as signals of coming weather. Though spiritual in interpretation, the phenomenon itself is scientific. Different bands contain slightly different manganese and carbonate compositions, causing wavelength-specific reflection. Inadvertently, these rituals treated the stone as a chromatic climate archive. Long before modern geochemistry understood its layering, the finest stalactites came from a small number of Argentine deposits, most of which are now closed, protected, or inaccessible. Modern geological conditions do not support the formation of new stalactites of comparable quality collectors. Therefore, value slices with flawless concentric symmetry, no radial fractures, vivid color transitions, minimal internal voids. Prices range from several thousand to more than $40,000, depending on diameter, color intensity, and band clarity. The market is not driven by speculation, but by geological finality. These structures are remnants of environments that will never reappear. Rhodochrosite stalactites endure as more than aesthetic minerals. They are fossilized stability, physical memories of a past Earth, preserved in rings that behave like the pages of a book long since closed. If rhodochrosite preserves time through delicate concentric memory, the next gemstone expresses Earth's legacy through mathematical precision, a crystal whose geometry appears engineered rather than grown. Ranked 14th, Jeremejevite, Azure Vector. Jeremejevite stands at the edge of mineralogical possibility. A crystal whose survival depends on a level of chemical precision, nature almost never achieves. Its pale blue prisms rise in perfect hexagonal symmetry, as if drafted by an engineer rather than grown from geological chaos. Jeremejevite does not simply crystallize, it aligns. And in doing so, it defies the inherent disorder of the environments that create it. Jeremejevite forms only when aluminum, boron, and fluorine meet in exact proportions inside granitic pegmatites. A surplus of aluminum disrupts the lattice. A trace of iron destroys the blue. A slight shift in temperature breaks the prism before it grows. Most pegmatites fluctuate too wildly. Chemistry drifts, cooling rates waver, pressure gradients collapse. Yet in a few locations in Siberia and Namibia, the variables converged with improbable precision, allowing Jeremejevite to assemble into elongated crystals so sharply defined that their edges appear machined. This is why the mineral is rare. Nature almost never maintains the chemical discipline required to grow it. Microscopic studies reveal faces with minimal distortion, refractive indices that remain stable across the entire prism, and cleavages that run with architectural regularity. Jeremejevite is the mineralogical equivalent of a perfect blueprint surviving a storm. Because of its geometric purity, early mineralogists in the 19th century treated Jeremejevite as a curiosity rather than a gemstone. Its clarity and elongated form earned it nicknames such as sky vector and direction stone, references to its arrow-like growth habit. In parts of Central Asia, traders once believed Jeremejevite guided journeys through deserts, not by magic but by association. Its straight, unwavering lines embodied focus and direction. In scholarly circles of the Soviet era, a specimen on a researcher's desk symbolized intellectual precision. An emblem of thought that refused to drift, Jeremejevite never became part of large cultural mythologies. Instead, it became a niche symbol among those who valued structure, intention, and exactness. Modern ritual practices involving Jeremejevite are less historical and more interpretive. Certain contemplative traditions place 6 crystals in a hexagonal formation, using the symmetry to represent decision clarity or the alignment of competing goals. Though not rooted in antiquity, the symbolism reflects the mineral's true nature. Jeremejevite exists because its internal geometry never deviated. Human ritual simply mirrors that truth. High-quality Jeremejevite is rare not because mining volumes are low, but because most natural crystals fail the threshold of perfection that collectors seek. Small faceted stones under 1 carat already reach high 4-figure prices. Anything above 2 carats crosses into the realm of extreme rarity, fetching over $20,000 due to both scarcity and the inherent difficulty of cutting such elongated crystals without fracturing them. Collectors prize Jeremejevite not for flamboyant color or optical tricks, but for the improbability of its existence. A mineral born only when hundreds of variables obey a single strict geometry. If Jeremejevite represents nature's precision at its most disciplined, the next gemstone reveals the opposite. A mineral whose beauty collapses the moment light touches it. Rarity defined not by perfection, but by fragility. Ranked 13th, Proustite, the gemstone that light itself destroys. Proustite is a gemstone defined by contradiction, a mineral that glows with internal fire yet cannot survive the light that reveals it. Its deep scarlet translucence, almost liquid in appearance, darkens, scars, and eventually collapses under exposure to sunshine. What makes it desirable also threatens its existence. Beauty and destruction are fused into a single equilibrium, one that collectors fear as much as they admire. Proustite is rare because it is fragile. And it is fragile because its atomic architecture resists the very conditions that make gemstones endure. Proustite forms within hydrothermal silver veins, where arsenic-rich fluids enter fissures at low temperatures. Its unique red glow arises from the way photons interact with arsenic sulfide chains inside the crystal. But this structure is unstable. When exposed to light, electrons within the lattice rearrange, triggering a slow transformation into a darker, degraded phase. This means every pristine specimen is a geological accident, preserved through improbable darkness. In places like the Ore Mountains, Chile, and Morocco, Proustite formed only when several rare conditions aligned briefly. But even then, few crystals survived extraction. The moment a vein was breached, sunlight often damaged the material before it could be collected. Its existence today depends not just on geology, but on geology combined with darkness, a double rarity. In medieval European mining towns, Proustite was known as feuerers, fire ore. Its blood-red gleam, visible even in dim torchlight, created legends of minerals that trapped the spirits of the mine. Miners avoided handling it unnecessarily, claiming it carried whispers or induced dreams filled with red shadows. These beliefs likely stemmed from arsenic vapors released when ore was heated, but folklore turned chemical danger into supernatural tension. Later, silver merchants prized Proustite not for beauty, but as a sign that rich silver deposits might lie nearby. Its appearance signaled wealth, but it also demanded caution. Its instability mirrored the unpredictability of the mines themselves. Superstitions warned against exposing Proustite to sunrise. Some communities believed daylight would wake the ore, releasing misfortune or illness. In some mining rituals, small fragments were wrapped in cloth and stored deep underground as protective offerings, never allowed to return to the surface. Though these rituals lack ancient origins, they capture an essential truth. Proustite is a mineral whose identity depends on remaining unseen. To preserve its beauty is to deny it visibility. In today's mineral market, collectors consider Proustite one of the most challenging specimens to maintain perfect crystals. Transparent, sharply terminated, and untouched by daylight, can reach $5,000 to $30,000 depending on clarity and size. But price alone does not define rarity. The true scarcity lies in the battle between preservation and inevitable decay. Owning Proustite is an exercise in tension. The collector safeguards a fire that is always trying to extinguish itself. If Proustite is a gemstone consumed by light, the next mineral is born from something far more violent. A stone created in a single instant when the sky itself strikes the earth. Ranked 12th, Fulgurite. Lightning turned to stone in a single breath. Fulgurite is the closest Earth ever comes to capturing the moment lightning touches the ground. It is a mineralized scar, hollow, twisted, and glass-bound, formed not over centuries but in a fraction of a second. Nothing about it is stable. Temperature, pressure, and motion collide in an instant too volatile for structure, yet a structure emerges. Its rarity does not lie in scarcity alone, but in the improbability that such violent conditions ever produce anything whole. A fulgurite begins when a lightning bolt delivers more heat than a volcanic eruption in a channel thinner than a branch. Temperatures spike to nearly 30,000 degrees Celsius, vaporizing air and liquefying sand along its path. The bolt tunnels downward like a plasma drill, melting silica into glass before the surrounding desert cools it so quickly that the molten material freezes mid-collapse. The result is a branching tube, sometimes straight, sometimes wildly contorted, lined with glass and filled with pockets of trapped air. Most strikes fail. The tube cracks, collapses, or never forms at all. A complete fulgurite is the aftermath of chaos arranged briefly into order. These structures can map the exact path of a single electrical discharge, preserving a geological event that lasted less than the blink of an eye. They are, in effect, fossilized lightning. Across Saharan trade routes, nomadic groups once carried fulgurites as proof that the sky could be caught. Traders believed the hollow tubes contained remnants of divine energy, the residue of a celestial impact. In medieval North Africa, fulgurites were associated with protection against desert spirits and sudden storms. Their twisted shapes were seen as roots of thunder, anchors of power pulled from the sky into the earth. Even earlier civilizations may have encountered fulgurites, but left sparse records, perhaps because their appearance was too irregular, too raw, too unlike typical minerals to be classified. Certain Berber traditions placed fulgurites near the entrances of tents during seasonal migrations. The tubes were believed to map the intention of the storm. A direct strike indicated conflict. A bent or forked form signaled journeys that might change direction. Though the rituals were symbolic rather than ancient, they reflect an intuitive understanding. Fulgurites are records of trajectories, of movement made visible. Modern esoteric groups treat fulgurites as conduits for manifestation rituals, interpreting their hollow interiors as channels for focused thought. While not historically grounded, these practices echo the mineral's true identity, a literal channel carved by energy and motion. Fulgurites are deceptively difficult to collect. Most shatter during extraction, others crumble under minimal pressure. Large intact specimens, especially branching tubes over 30 centimeters, are exceptionally rare and can command thousands of dollars smaller. Unbroken segments are more accessible but still valued for their symmetry and integrity. Collectors seek fulgurites because they are unique to a moment. No two bolts strike alike, no two tubes twist alike, and no two specimens can ever be recreated. Artificial fulgurites exist, but their smooth or overly uniform interiors betray their origins instantly. True fulgurites are prized not for color or transparency, but for narrative. They are geological eyewitnesses to a singular, violent birth. If fulgurite embodies creation through instantaneous violence, the next gemstone reveals a legacy forged far deeper, a crystal that carries the memory of oceans, swallowed by the earth itself. Ranked 11th, diamond type IIb, the blue core born from drowned oceans. Among all diamonds, Type IIb stones stand apart not for brilliance, but for the secret they carry. They contain boron, an element that should not exist anywhere near the depths where diamonds form. Their blue cores are more than aesthetic anomalies. They are geological revelations, proof of oceans dragged into the mantle and preserved under conditions once thought incompatible with gemstone formation. Type IIb diamonds are rare not merely because they are few, but because their very existence rewrites our understanding of Earth's interior. Most diamonds form 150 to 200 kilometers beneath the surface, where carbon is compressed into crystalline order. Type IIb diamonds originate deeper still, near the mantle transition zone, where pressures exceed 20 gigapascals and temperatures rise beyond 1,500 degrees Celsius. At such depths, boron has no natural source. It should not be present. Yet microscopic analysis shows boron atoms threading through the carbon lattice, bending the diamond's optical path and producing its electric blue hue. The only explanation is a revelation in itself. Ancient oceanic crust, containing boron-rich minerals, was subducted into the mantle millions of years ago. There, the element survived crushing heat and pressure long enough to be incorporated into growing diamonds. When kimberlite eruptions later blasted these diamonds upward, they carried with them a record of drowned continents and vanished seas. Type IIb diamonds are therefore geological messages, fragments of oceanic history preserved in crystalline form. In early Indian courts, blue diamonds were believed to hold the memory of sunken empires, remnants of worlds destroyed by monsoon gods. Scholars translated their hue as a sign of depth, physical, spiritual, and historical. Persian astronomers associated them with celestial balance. Their blue cores were thought to mirror the equilibrium of cosmic cycles, and rulers wore them during astronomical ceremonies to invoke clarity and judgment. Unlike other famed gemstones, Type IIb diamonds were never symbols of opulence alone. They were treated as artifacts from below the oceans and above the heavens, occupying a space between myth and geology. In the modern market, Type IIb diamonds occupy the highest tier of rarity. Just a few sources, primarily historic mines in India and South Africa, have produced them. Even then, the proportion is microscopic, far below 0.1% of all diamonds mined. Auction prices reflect scarcity paired with narrative weight. Small stones command six-figure values. Larger vivid blue specimens routinely exceed tens of millions. Much of the value comes from what they represent, a geological origin so unlikely that every diamond is, in effect, a scientific anomaly. Collectors do not merely buy color, they buy a documented impossibility. If Type IIb diamonds reveal truths buried in the planet's deepest past, the next gemstone demonstrates a different form of improbability, a mineral whose very presence can redraw the boundaries of geological maps. Ranked 10th, Grandidierite, the threshold gem that redraws Earth's geological map. Grandidierite is a gemstone shaped not only by geological forces, but by the consequences of its own existence. Every discovery, each a small teal-blue window into the Earth's hidden chemistry, has shifted scientific assumptions about how minerals form along ancient continental fractures. Grandidierite is rare, but rarity alone does not define it. Its scarcity is tied to something deeper. The stone appears only where the crust records violent metamorphic events, places where landmasses collided, sheared, and transformed under pressures strong enough to rearrange entire mineral systems. Wherever grandidierite emerges, it changes the map. Grandidierite forms almost exclusively within metamorphosed pegmatitic zones, where aluminum, boron, and magnesium converge under extreme conditions. These environments cannot be predicted. They must be inferred from scars in the crust, folds, faults, and pressure shadows left behind by the slow grinding of tectonic plates. The mineral's signature color, a shifting gradient of blue, green, and teal, results from complex interactions between iron and boron within a distorted lattice. For this structure to stabilize, temperature and pressure must follow a precise path during metamorphism. Deviate slightly and the crystal breaks down or transforms into different minerals entirely. This dependency on geological crossroads is why grandidierite appears sporadically across Madagascar, Sri Lanka, and a handful of islands in the Indian Ocean. Each location tells the same story, a violent past frozen in crystalline form. The gemstone is not just a product of metamorphism, it is a witness to consequences set in motion millions of years ago. In communities along Madagascar's southern coast, grandidierite was once regarded as a boundary stone, a token of transitions. Locals believed its shifting color symbolized the space between land and sea, body and spirit, memory and forgetting. It was sometimes placed near doorframes during rites of passage, marriage, departure, or mourning, serving as a quiet marker of change. While these customs remained localized and never developed into widespread mythology, they reflect an instinctive understanding. Grandidierite does not belong to static landscapes, it appears where the earth has been remade. Although symbolic, the ritual mirrors the mineral's geological truth. Grandidierite only forms in environments undergoing profound transformation. Its very presence indicates a threshold crossed. Grandidierite is one of the few gemstones whose price is not dictated solely by color or clarity, but by origin. Because each deposit forms under unique tectonic conditions, stones from different regions show distinct optical signatures. Faceted stones above 1 carat are extremely rare. Above 2 carats, exceptional prices climb into 5-figure territory for transparent material, with ultra-rare, vivid blue stones entering the 6-figure range. Collectors value grandidierite not only for scarcity, but for what scarcity signifies: a geological event recorded in mineral form. In gemstone markets, few materials exert such influence. A new discovery does not flood supply. Instead, it revises scientific understanding of the region's geological past. The gemstone forces cartographers and mineralogists alike to reconsider the subterranean history of its homeland. If Grandidierite marks the consequences of ancient collisions, the next gemstone reveals something stranger, a mineral so anomalous that it was first identified only after it had already been cut. Ranked 9th, Taaffeite, the double shadow gem, born from a geological mistake. Taaffeite entered the world of mineralogy through a mistake. In 1945, a gem already cut and polished, thought to be a simple spinel, caught the attention of Count Richard Taaffeite. It refracted light in a way no spinel should. Its birefringence produced a faint double shadow, an optical signature belonging to no known gemstone at the time. Only later would scientists confirm the truth. The cut stone was not misidentified, it was unprecedented. Taaffeite is an anomaly not only in origin, but in structure. It occupies a chemical and optical space between spinel and chrysoberyl, yet matches neither. It should not exist because the mineralogical pathways that create it are vanishingly rare. Too much pressure and its lattice collapses into chrysoberyl, too little, and it forms spinel instead. Taaffeite is the improbable midpoint, an interstitial mineral born of perfect imbalance. Taaffeite's formation requires an intersection of conditions never expected to coexist. Magnesium, beryllium, and trace iron must fuse within a pegmatitic environment, but the pressure and temperature must follow a narrow, unstable corridor between two established mineral systems. If the environment shifts slightly toward higher pressure or boron concentration, chrysoberyl forms. If it tilts toward lower aluminum or magnesium, spinel emerges. Taaffeite is the sliver between them, a crystallographic error that nature almost always corrects. This explains why the mineral was discovered only after cutting, and why most deposits produce microscopic grains, at best transparent crystals large enough for facetting, are extraordinarily rare. With Sri Lanka and Tanzania producing the only known gem-quality specimens in notable quantity, its optical anomaly, weak but measurable double refraction, makes Taaffeite a mineral caught between identities. A gemstone with two shadows. In Sri Lankan lapidary circles, Taaffeite is sometimes called the missing gem, referencing its initial discovery outside the mine rather than within it. For cutters, it represents humility, a reminder that even familiar material may contain surprise. Its cultural weight lies not in ancient ritual, but in its status as proof that mineralogy still encounters the unknown. Modern metaphysical groups often use Taaffeite to represent liminality, thresholds between states, forms, or identities. Its dual shadow refraction is interpreted as the coexistence of possibilities. Taaffeite's rarity exceeds that of most gemstones considered precious. Faceted stones above 1 carat are extremely uncommon. Those above 2 carats approach mythical status. Prices fluctuate dramatically due to scarcity. Small transparent stones may begin at several thousand US. Larger, unheated, vividly colored stones can reach tens of thousands. Fine specimens above 3 carats enter six-figure territory. The market is further complicated by misidentification. Many pieces remain mislabeled as spinel. Undiscovered taaffeite likely sits in old collections, hiding behind incorrect tags. Another anomaly in its story. Collectors pursue the stone not only for beauty, but for the narrative embedded in its discovery. A gem found only because it refused optical norms, revealing itself through an error in expectation. If Taaffeite represents nature's quiet defiance of classification, the next gemstone embodies something far older. A material shaped not by crystal chemistry alone, but by forests that vanished millions of years ago. Ranked 8th. Blue amber. The last light of a forest that no longer exists. Blue amber is not a gemstone shaped by pressure or heat, but by time, and by forests that disappeared long before humans arrived. Its blue luminescence is not an inherent color, but a phenomenon, a relic of vanished ecosystems encoded into fossilized resin. When sunlight or UV strikes its surface, the amber emits an otherworldly azure glow, as if releasing the last memory of a lost woodland. Blue amber is rare not because amber is scarce, but because the specific chemical signatures that create its blue radiance no longer occur in nature. It is the light of something that should not exist anymore. Blue amber originates primarily from the ancient Hymenaea trees of the Miocene era. Trees that once grew across regions now submerged or eroded into oceanic basins. Their resin contained unique polyaromatic compounds. Over millions of years, as the resin fossilized into amber, these compounds became fluorescent under shorter wavelengths of light. Dominican deposits contain it sparsely. Indonesian ones display it unpredictably. And once exposed to environmental stress or oxygen intrusion, the fluorescence fades. Geologists often describe blue amber as the preserved memory of an ecosystem, for it carries chemical signatures from forests that have no modern analog. In the Dominican Republic, Early Taino communities prized amber not for color, but for its warmth and buoyancy. Blue amber, when encountered, was believed to contain captured fragments of sky fragments were worn during ceremonies that honored origins and migrations, serving not as amulets but as reminders of lineage tied to land. Some rituals involved placing blue amber near flame. The flickering yellow light suppressed its natural fluorescence, making the stone appear inert. When the flame was extinguished, the blue glow returned. This contrast, light that vanished and reappeared, was interpreted as evidence of dual worlds, the world seen and the world remembered. Scientifically, the effect is caused by Rayleigh scattering and the presence of aromatic hydrocarbons absorbing and re-emitting energy. Yet the symbolism aligns perfectly. Blue amber reveals only when conditions mimic the light of the forest canopy that originally produced it. True blue amber is rare, not because deposits are small, but because its chemistry cannot regenerate. The trees responsible are extinct, the ecosystem's gone. The exact microbial and sedimentary conditions, unreproducible fine specimens can reach thousands to tens of thousands of dollars, depending on size and intensity of glow. No two pieces display identical fluorescence patterns. Each is a unique, fossilized record of a lost environment. Blue amber's value comes not from rarity alone, but from its irreversibility. It is the sunlight of forests erased by geological time. We have crossed through minerals defined by geometry, fragility, violence, and memory. With blue amber, the story shifts. From this point onward, the gemstones grow increasingly improbable, formed in pressures that distort crystal identity, in volcanic fractures that exist only for seconds, in chemical windows that barely stay open. The next gemstone begins this new phase. An emerald born not in calm veins but in hydrothermal torrents fierce enough to tear its chemistry apart, and yet somehow create order. Ranked 7th. Hydrothermal. Emerald, the gem, born in pressure that should have destroyed it. Hydrothermal emeralds form in a geological environment so unstable that their existence borders on contradiction. They are born not in calm mineral veins, but in violent hydrothermal systems, superheated fluids rushing through fractures with enough force to tear apart lesser minerals. In these narrow windows, where temperature and pressure fluctuate between creation and destruction, Beryl molecules manage the impossible. They incorporate chromium or vanadium, crystallizing into emerald before the chemistry collapses again. This is the paradox, a gemstone forged in a place where gemstones should not survive. Classic emeralds grow in long-lasting veins where pressure is stable and chromium-rich fluids migrate slowly. Hydrothermal emeralds are the opposite. They require supercritical fluids exceeding 500 degrees Celsius. Rapid, fluctuating pressure, sudden chemical mixing between incompatible rock types, fractures that open and reseal within hours. Chromium or vanadium entering solution at the exact moment Beryl nucleates. These conditions rarely coexist. Most hydrothermal systems either destroy emerald before it forms, or form Beryl too pale to be recognized. Yet in Colombia's Muzo and Chivor zones, and a handful of anomalous deposits worldwide, the chemistry aligns so precisely that emerald emerges as a byproduct of geologic violence. Hydrothermal emeralds preserve within their fluid inclusions micro-droplets of the same superheated brine that formed them. Tiny relics of catastrophic pressure events. For geologists, these inclusions act as time capsules of the Earth's most dynamic hydrothermal phases. Unlike classical emeralds, long interwoven with myths of kings and fertility, hydrothermal emeralds never built deep folklore. Instead, they became symbols among miners and gem cutters of the land's volatility. In Colombian mining communities, emeralds formed in fast-moving fluids were referred to as piedras de tormenta, storm stones. The term does not describe color or clarity, but origin. Minerals born where the earth boils. Miners believe stones with sharply angular growth zones held unfinished energy, remnants of the turbulent fluids that carried them upward. Hydrothermal emeralds thus entered culture not as emblems of royalty, but as emblems of geological rebellion. The value of hydrothermal emeralds is shaped by two forces, geological rarity and optical unpredictability. Because formation conditions are erratic, high-quality crystals appear sporadically and without pattern. Many emeralds from hydrothermal zones show intense color zoning internal pressure fingerprints, multi-phase inclusions containing ancient gas and brine, terminations distorted by fluctuating chemistry. Such features, once seen as flaws, are increasingly prized by collectors for their geological storytelling. Fine specimens from Colombia with strong saturation and minimal fractures can command significant prices, rivaling more traditional sources. What collectors seek is authenticity, a stone whose inclusions reveal a genesis so chaotic that the emerald itself feels improbable. Every hydrothermal emerald is a record of pressure that nearly exceeded emerald's ability to exist. If hydrothermal emeralds survive the turbulence of rising fluids, the next gemstone is forged even more precariously. In narrow volcanic fractures where the window for crystallization lasts only, ranked 6th, red beryl, the gem forged in a volcanic window that almost destroyed it. Red beryl is a gemstone born from conditions so narrow and unforgiving that its creation resembles an act of geological sacrifice. It forms in fractures beside volcanic vents, windows that open for moments, then close forever. Temperatures rise high enough to destroy beryl formation, pressures drop low enough to prevent chromium incorporation. Yet for reasons still debated, a handful of fractures in the American Southwest stabilized just long enough for chromium to diffuse into growing beryl crystals, producing one of the rarest hues on Earth, a saturated incandescent red. Red beryl does not simply exist, it survives. Emerald and aquamarine form through the predictable chemistry of beryl. Red beryl does not. Its chromatic signature demands conditions at odds with beryl stability. Volcanic gases delivering chromium in fleeting pulses, fractures heated by rhyolitic magma low-pressure pockets, preventing the crystal from dissolving, hydrothermal fluids entering at the precise interval between thermal surges. If the fracture is too hot, beryl dissolves. If too cool, chromium never enters the lattice. If the magma shifts, fractures collapse. Red beryl's formation window is so narrow that even within the same volcanic field, one fracture yields crystals, while another only meters away produces none. Most known red beryl comes from the Wah Wah Mountains of Utah, a place where volcanic flows, hydrothermal veins, and gas channels merged in an improbable balance. Each crystal is a frozen moment of geological negotiation. Indigenous groups of the Southwest left few direct records referencing red beryl, but oral traditions speak of stones, born from the exhale of fire, carried by spirits living beneath volcanic mesas. These tales likely emerged from encounters with vivid red minerals in rhyolitic terrains. Later, early settlers interpreted the stone's scarcity as evidence of hidden strength. In mining folklore, red beryl became associated with endurance, the ability to withstand destructive forces and emerge transformed. The surrounding landscape supported this symbolism: red mesas, volcanic ridges, and faulted valleys shaped by slow-burning violence. Rather than mythologized treasure, red beryl became a quiet emblem of resilience. Red beryl is sometimes called the red emerald, though the comparison is misleading. Emeralds form across continents. Red beryl forms only where a set of contradictions briefly align. Gem-quality crystals are microscopic, often measured in millimeters. Stones above 1 carat are extremely rare. Stones above 2 carats are museum-grade and approach mythic status. Prices reflect this near impossibility: thousands of dollars per carat for modest specimens, and far higher for intensely saturated stones. Collectors value red beryl not only for color, but for the reality that the Earth will not make more. The volcanic systems that produced it are dormant or eroded, the fractures sealed, the hydrothermal pathways extinguished. Red beryl is a gemstone shaped by the planet's willingness to hold open a fragile window, one that closed almost as soon as it appeared. If red beryl is born through sacrifice, surviving conditions that nearly erased it, the next gemstone shifts from survival to contradiction. A mineral that exists because its chemistry defies the boundaries of its own family. Ranked 5th, Pezzottaite, the raspberry gem formed by a chemical glitch in Earth's crust. Pezzottaite is a gemstone that should have belonged to the beryl family, and yet, at a structural level, it does not. Its vivid raspberry color, its trigonal symmetry, its unusual refractive behavior all mark it as an outsider, a mineral that mimics beryl while subtly rejecting the rules that define it. First discovered in Madagascar in the early 2000s, Pezzottaite appeared as an anomaly from the very beginning, a crystal too pink, too refractive, too structurally distorted to fit into the established taxonomy of beryl. Pezzottaite is rare not because the Earth produced little of it, but because the conditions needed to distort beryl into pezzottite existed only briefly, and may never exist again. Under these contradictory influences, the beryl lattice buckles and reconfigures into a trigonal system. Cesium atoms enter positions beryl does not normally allow, forcing the crystal to stabilize in a geometry that mineralogists had never documented in nature. In essence, Pezzottaite is a crystallographic misfire, a rare moment when environmental stress produced stability instead of destruction. Because of its recent discovery, Pezzottaite has no ancient folklore. Yet in Madagascar, miners refer to it as Vato Misaina, the thinking stone, a reference not to mysticism, but to its puzzling contrast with beryl. It looks like beryl, behaves like beryl, forms where beryl should appear, and yet diverges at the final moment as if making an unexpected choice. In gemological circles, Pezzottaite became a symbol of humility, a reminder that mineralogy, even in the 21st century, can still encounter materials that slip between definitions. It represents the quiet truth that Earth's chemistry is not bound by human categorization. Modern metaphysical practices, though not rooted in ancient tradition, interpret pezzottite as a stone of deviation and transformation. Its trigonal geometry is seen as an emblem of divergence from expectation, a mineral that took another path. Symbolism aside, the sentiment aligns with geological reality. Pezzottaite's identity is built from a structural detour, a moment when beryl chemistry abandoned its usual symmetry and created something entirely new. Pezzottite's scarcity is absolute. The pegmatitic fields of Madagascar that produced the first significant finds have largely exhausted Afghanistan, and Myanmar yielded small discoveries, but none with long-term production potential. Because the stone occupies an awkward space between beryl and its own identity, early markets struggled to categorize it. But once recognized as a distinct mineral species, prices surged. Fine stones over 1 carat command high 5-figure prices. Clean specimens over 2 carats approach 6 figures. Unlike classic gemstones with recurring geological opportunities, Pezzottaite's formation relied on a rare chemical glitch in Earth's crust. Once that environment changed, the possibility of new material nearly vanished. Its value lies not only in beauty, but in the geological moment it represents. A brief interval when the planet produced a mineral that sits between categories, a gemstone created by anomaly rather than order. If Pezzottaite is the anomaly born from structural deviation, the next gemstone magnifies that deviation into complexity. A mineral whose internal architecture is so intricate that recreating it has defied science for decades. Ranked 4th, Serendibite, the midnight crystal built from impossible precision. Serendibite is a gemstone defined by structural complexity so extreme that its very formation feels improbable. Its lattice hosts aluminum, calcium, boron, magnesium, and a constellation of other elements in arrangements that challenge mineralogical symmetry. Most environments cannot assemble such a structure without collapsing into simpler silicates. Yet in 2 locations, Sri Lanka and Myanmar, Earth briefly achieved the precision required to create crystals deep blue-black, dense, and optically elusive. Serendibite is rare not simply because deposits are small, but because the precision needed to build it almost never occurs in nature. Serendibite crystallizes within skarn environments, contact zones between intrusive magma and limestone, where mineral reactions proceed in rapid, turbulent waves. Serendibite is named after Serendib, the old Arabic and Persian name for Sri Lanka, meaning island of jewels. Though the stone itself has no ancient myths, the land beneath it does. Sri Lanka's skarn belts were revered for producing materials that defied normal classification, stones darker than night, yet carrying hidden internal reflections. Local lapidaries sometimes refer to Serendibite as the midnight edge, describing the way its deep tone seems to cut darkness rather than reflect light. Among cutters, it became a symbol of mastery because shaping a mineral this hard, this brittle, this resistant to polish demands precision, echoing the precision of its own creation. Modern ritual uses of Serendibite focus on discipline, focus, and thresholds. Practitioners often position the stone at transition points, door frames, meditation boundaries, or liminal spaces, to symbolize the ability to hold structure under pressure. While not historically rooted, the symbolism harmonizes with geological truth. Serendibite is a mineral whose identity depends on maintaining integrity at the edge of instability. Its existence is itself a ritual of balance. True gem-quality Serendibite is among the rarest gemstones ever found. Sri Lanka's deposits are ancient, small, and largely depleted. Myanmar's discoveries remain limited and unpredictable. Faceted stones above 1 carat approach legendary status. Stones above 2 carats enter the realm of museum rarities. Value reflects scarcity, but also difficulty. Serendibite resists cutting due to density and cleavage. Only a small percentage of rough converts into faceted gems, and even then, the result is subtle. Deep, almost opaque stones with flashes of blue and green appearing only under intense light. Collectors prize Serendibite not for brilliance, but for structural impossibility. It represents a mineralogical convergence that should collapse under its own complexity, yet for a brief geological moment remained intact. Prices for clean, well-cut stones start in the tens of thousands and escalate dramatically with size. But more than wealth, Serendibite offers something rarer, a fragment of perfect geological balance preserved within darkness. If Serendibite embodies precision, held together by complexity, the next gemstone shifts from structure to obsession. A crystal once believed to be so rare that only a single specimen existed for half a century. Ranked third, Painite, the extinction gem that sparked a global obsession. For more than half a century, Painite held a position no gemstone had occupied before. It was believed to exist as one single crystal, not one deposit, not one mine, one specimen. Its identity, confirmed in the 1950s, placed it in a mineralogical category of near extinction. The rarity was so absolute that Painite ceased to be a gemstone and became a mystery, an object of pursuit for collectors, scientists, and fortune hunters. Painite is rare not just in quantity, but in the obsession it created, a gemstone whose existence challenged both discovery and desire. Painite forms in environments few minerals can survive. It requires boron and zirconium, two elements with limited coexistence, to crystallize together within a matrix of calcium, aluminum, and oxygen. The conditions under which these elements combine are so restrictive that even geologists struggle to model the process. Most geological systems disrupt the process long before Painite can stabilize. The boron escapes, zirconium crystallizes into other minerals, or the structure fractures. Painite requires conditions at odds with its own chemistry, a geological contradiction allowed to exist only by chance. For decades, even regions known for complex pegmatites failed to produce new finds. Painite seemed extinct before it was even understood. Painite has no ancient mythology. It is too new, too rare, too elusive. Instead, it acquired something different, a legend forged in laboratories, auction houses, and whispered networks of gem hunters. Collectors spoke of Painite as the impossible stone, the one mineral that could complete a collection few dared attempt. Museums pursued clues about its origin. Gemologists debated whether more specimens would ever appear or whether the first discovery was a singular geological accident. Painite became a symbol not of power nor beauty, but of completion, the ultimate piece in the puzzle of Earth's mineral diversity. Though Painite lacks ancient rituals, modern culture created new ones. Gem conferences treated the unveiling of each new specimen as a ceremonial event. Collectors gathered around display cases as if witnessing a rare celestial alignment. Online forums developed rites of initiation. To see Painite in person became a milestone in a mineral enthusiast's life. These rituals, though contemporary, reflect something fundamental. Painite inspires behavior normally reserved for sacred objects. Before the early 2000s, Painite held a Guinness World Record as the rarest gemstone on Earth. Only after new deposits were uncovered in Myanmar did more specimens reach the market. But even then, the supply remained microscopic. Today, faceted Painite gems above 1 carat are extremely rare. Stones with strong red saturation are rarer still. Prices vary widely, shaped by color, clarity, and size. But fine gems command 5 to 6-figure sums with ease. Yet value is not defined by scarcity alone. Collectors pursue Painite because it is a gemstone that almost never existed, a mineralogical near-extinction event preserved in crystalline form. For many, owning Painite is not about aesthetics. It is about holding a fragment of a decades-long global obsession, an object that redefined what rare means. From a gemstone that inspired obsession, we move to one that defies identity. A garnet capable of shifting color with such dramatic precision that it seems to contain two worlds at once. Ranked second, blue garnet, the color-shifting gem, born from an impossible element. Blue garnet is a contradiction made visible, a gemstone that defies its own mineral family. Garnets are known for reds, oranges, greens, and rare purples, but never blue. The chemistry of their lattice resists the wavelengths required to produce a true blue hue. Yet near the dawn of the 1990s, in a small region of Bekyele, Madagascar, garnet crystals emerged that shifted from teal blue in daylight to violet red under incandescent light. This was not mere color change, it was a spectral inversion, a garnet that behaved like two different minerals depending on the light it encountered. Blue garnet exists not because nature allowed it, but because, briefly, the consequences of mantle chemistry tipped into the improbable. The garnet group typically incorporates iron, manganese, magnesium, aluminum, chromium. Vanadium, however, rarely integrates into the garnet lattice at concentrations high enough to alter color. Blue garnet is not just a rare garnet, it is a geological consequence, the improbable result of vanadium forcing its way into a structure that almost never accepts it. Blue garnet is too new to carry ancient myths, but its dual spectral behavior quickly inspired contemporary symbolism. In East African lapidary culture, cutters began calling it Miviri Miwili, the twin-bodied stone. Its shifting colors became metaphors for choice, identity, in the coexistence of opposing truths. In gemological circles, blue garnet became an emblem of the unexpected. For decades, textbooks stated that garnets cannot be blue. Blue garnet arrived as a quiet correction. Its cultural footprint is modest but distinct, a stone that reminds observers that classification is temporary. Some modern practitioners use blue garnet in dual light rituals, where stones are moved between natural daylight and flame-lit environments. The transitions, cyan to violet, blue to crimson, are interpreted as the unveiling of hidden aspects of the self. The ritual may be contemporary, but it aligns with scientific truth. Blue garnet's identity is inseparable from the light that touches it. Without illumination, its paradox remains unseen. Blue garnet is one of the rarest garnets ever mined. High-grade stones above 1 carat are uncommon. Stones above 2 carats approach museum status. Stones above 3 carats are nearly unheard of. Prices reflect this near impossibility. Fine stones command 5 figures per carat, while exceptional specimens enter 6-figure territory. But the true value lies deeper. Blue garnet is a spectral anomaly, a gemstone whose existence proves that even well-defined mineral groups can fracture under the right geologic pressure. Its market is shaped not by hype, but by the reality that the conditions which produced it are neither stable nor self-renewing. Every blue garnet is a record of a chemical event that may never occur again. We now stand at the threshold of the impossible. The gemstones so far have challenged structure, chemistry, pressure, and light. But the final stone goes further, not by dazzling the eye, but by retreating into silence, a mineral so rare that even in the scientific community, it is spoken of quietly. A presence defined by absence. In first place, Musgravite, the impossible gem that rose quietly from the mantle. There are gemstones that dazzle, gemstones that defy, and gemstones that challenge classification. Musgravite does none of these. It simply appears, quietly, sparsely, like a geological whisper rising from the deepest fractures of the earth. Its rarity is not measured by scarcity alone, but by silence. The lack of deposits, the absence of reliable formation data, the near emptiness of records describing where it truly comes from. Musgravite does not reveal itself. It allows itself to be found only in traces. It is the gemstone that should not exist because the conditions beneath the mantle crust boundary rarely allow minerals this stable, this transparent, this orderly to survive the journey upward. And yet it does. Some geologists describe musgravite as an upper mantle orphan, a mineral lacking a complete origin story because the environment that formed it no longer exists. Musgravite does not announce its past. Its past has already faded. Musgravite is too rare, too recent, too silent to have folklore. Instead, it became a symbol among gemologists of the unseen earth, the layers beneath continents where pressure writes its own grammar, indifferent to human time. Collectors often speak of musgravite without superlatives, not as treasure, not as symbol, but as presence, the kind that suggests the earth holds far more secrets than it reveals. In conversations, musgravite is described the way one might describe a distant star seen only once through a telescope, with restraint, with humility, with a sense that any claim about it must be tentative. Modern metaphysical groups rarely use musgravite. Most have never encountered it, and those who do treat it not as a tool, but as an object of contemplation, a mineral for stillness, for thresholds, for the quiet before transformation. Pieces are placed in empty rooms, on bare surfaces, with no candles or symbols, nothing that distracts from the stone's singular truth. It does not ask to be interpreted. The ritual is absence itself, a listening. This practice, though contemporary, echoes the stone's nature. Musgravite is not expressive like opal, not radiant like diamond, not flamboyant like tourmaline. It is a mineral whose identity arrives in silence and stays in silence. Musgravite is often compared to Taaffeite, but the comparison is misleading. Taaffeite is rare. Musgravite is almost theoretical. Faceted stones above 1 carat exist, but in numbers so small that estimates vary. Some say dozens, others say fewer. The true count is uncertain because musgravite often sits misidentified for years, quiet even in discovery. Its value cannot be charted by typical market behavior. Prices are high, 6 figures for fine stones, but the market lacks volume, rhythm, or predictability. Every sale is an event, not a trend. Every specimen is a singularity. Collectors do not buy musgravite for color. Its gray-violet spectrum is subtle. They acquire it because somewhere along the Earth's deep fractures, a mineral formed that by all logic should have dissolved, altered, or never reached the surface at all. Musgravite is the impossibility that survived. Even now, its origin remains incomplete, its pathways uncertain, its future supply almost certainly empty. So musgravite stays as it always has, a quiet fragment of the mantle, a mineral shaped by pressures too deep to describe, a presence defined by what it refuses to reveal. Everything else is silence. The journey ends where the earth grows quiet. 15 stones, each an exception, a contradiction, a moment when pressure, heat, chemistry, or time briefly broke its own rules. Some were born in darkness, some in violence, some in windows of opportunity so narrow they may never open again. And one rose from the mantle in near silence, a reminder that even today, the planet is still writing chapters we have not yet learned to read. If these stones teach anything, it is that rarity is not about beauty or value, but about survival against probability. Thank you for walking through these impossible fragments of the earth. Before you leave this hall of stories, a quiet question remains. Which of these 15 stones felt the most impossible to you, and why do you think it survived at all?